FYDP Group 1. What we're working on is scaling up the cathode of a zinc-ion battery. The motivation for this project is that, as excited as everyone is about the progress in renewable energy, solar and wind have a downside. The sun doesn't always shine, the wind doesn't always blow, which means that the best way this is shown in what's called a duck curve, because for grid operators, apparently this looks like a duck. But what it shows is as you have more and more solar on the grid, you get like a total oversupply of electricity in the middle of the day, and then you still have nothing to address when people start their day in the morning and when they get home at night. And what that translates into, and we've seen this in California and Germany, is you get more and more solar, and then they make less and less money, and then you just still have to build more coal and natural gas plants. So we aren't actually going to be solving the problem with global warming if this isn't solved, and the way you solve it is with batteries. So you put a bunch of batteries in the electrical grid, and then you can charge these batteries with the wind and the sun and use that electricity whenever you want. So that's a big picture thing that we're going after. The current solution is lithium-ion. This is the best battery in the world because it's had decades of development. But it was made for laptops and cell phones. So it was made to be light. It was made to be light, compact. And we're going into a market where they don't care about weight and volume. So there's an opportunity here, especially because the thing that makes lithium-ion great, which is its high voltage, leads to its downside. So the high voltage of these batteries constantly consume their contents, and that's why you have a limited life. And there's a big fire risk because you're using flammable components in a flammable liquid. And Samsung showed us how bad this can get. The major challenge to innovating in the battery space is that for all its shortcomings, lithium-ion is the technology to beat, and its costs are coming down precipitously. And it's very hard, if you're scaling up your own technology, to compete with this cost curve. So the high-level challenge is how do we make a lower cost, better performing battery that can actually use lithium-ion manufacturing? Because you're not going to beat lithium-ion manufacturing. You're not going to beat that cost curve. But if you can ride it down, you can actually get to market. And this is the solution. So this is a zinc-ion battery. It came out of research in the Nazar lab at Waterloo. It uses zinc metal as the negative electrode, a water-based electrolyte, and then a unique layered material that enables the reversible intercalation of zinc. So zinc ions come into the crystal structure, undergo an electrochemical reaction, and then they come out. And this material is really key to the whole thing. It's the presence of interlayer water is what allows the zinc ions to actually travel through the crystal structure. So making this material and getting it to work in a cathode is kind of the key challenge. It also enables the long cycle life of the battery. So again, if you want to beat lithium-ion in this application, you need to show a longer service life. So that's kind of where the technology was. So there's a good proof of concept that it works and it has a long life, and because it's water, it's safe, and the material set is cheaper. But the key problem and where the science stops and where the FYDP begins is that they made it a lab scale method that's non-scalable. So our key challenge of how are we going to beat lithium-ion? We have to use lithium-ion manufacturing. That's been completely unaddressed. And so that's the goal of this FYDP is let's take this technology that's been proven, that works, that's exciting. Let's make it in a way that's scalable, and let's actually scale up the components so that they can hit the cost targets and there's actually a commercially viable product here. So that's the background. I'm going to hand it off to Austin to explain how well things went.
All right, thank you, Ryan. So first I'm going to talk about the primary goal of the FYDP, and that was increasing areal capacity. So areal capacity is a function of mass loading and specific capacity, and in our FYDP's case, the areal capacity of the cathode determines the amount of energy in every cell of the battery, which means that it has quite a large effect on overall cost. As we can see in this curve, the cost per kilowatt hour decreases with an exponential decay as areal capacity increases. To lighten the focus of our FYDP, we constrained ourselves to working with the standard lithium-ion process because, as Ryan mentioned, you just can't beat how good the process is. For our secondary goal, we were determined to develop a scalable synthesis for these batteries, and at the start of the FYDP, the zinc vanadium oxide synthesis method was actually based off of, involving something called hydrothermal synthesis, which involves high temperature and pressure over a long period of time. And this was undesirable because of its high cost and also with the fact that we could only work with a maximum of 15 millimoles of the amount of our material, which isn't very good for scaling up. And what we found through our analysis is that the cost per kilowatt hour with respect to the processing cost of the active material decreases with quite a linear relationship. So now I'm going to talk a bit more about the results of our FYDP in more detail. One of the first things that our group was able to do was we were able to increase mass loading to our targets, that being a mass loading of 30 milligrams per centimeter squared. Based off of the Nature paper, if we were to have the demonstrated capacity of 300 milliamp hours per gram, we would have the 10 milliamp hours per centimeter squared for areal capacity that we needed. However, we're only able to reach or demonstrate 175 milliamp hours per gram. Some of the cathodes even had poor adhesion to the nickel foil and also incurred cracking. One other thing that our FYDP group did is that we developed an alternative synthesis by testing out two alternative methods. One of them was oxidation with peroxide, and the other was a reflux synthesis. Unfortunately, the peroxide oxidation method resulted in something called a redox shuttle, which means that when the cathode was dissolved in the water-based electrolyte, it would basically charge forever, which obviously doesn't make for a very good battery. The reflux method, however, on the other hand, produced a more ideal case in which the cathode was non-dissolving in water. So that was good. In terms of the cost for our fabrication process, we noticed at the beginning of our FYDP that the total cost per kilowatt hour was around $11,000, which was quite high and obviously not at the level that it could be for marketing. So through our group's work in maximizing areal capacity and optimizing the synthesis process, we brought down the cost to around $266, which is close to the target of $217 that we noticed for the bottom of the lithium-ion curve shown on one of the previous slides. So what are some lessons learned from this FYDP? Well, one of the big ones is that managing equipment lead times is a pretty important matter that should be well considered during the course of the project, as delays in the equipment can result in a whole schedule being pushed back, as there are multiple failure modes that can be incurred. As well, the drying protocol for our batteries also needs a lot of attention, as this will determine how well the battery operates once it's in its casing. Some of the next steps for this FYDP, if it were to continue, would be to modify the reflux reaction parameters in order to increase the production of them. And these includes factors like temperature, concentration, and reaction time. Another factor involved would be including different conductive additives to improve the electrode-specific capacity of these batteries. Thank you for your time, and that's all we have. We'll take any questions that you have at this time.